So we had Vincent here, right, for NERC. I like the talk. Are you presenting some of that as well?
Yeah. Yeah, that'll be the second portion of the talk.
Yeah, but not the generalization. The generalization is different.
Yeah. Yeah, actually, I'm curious to it. Yeah, I'd forgotten that he was here.
Yeah. I mean, it's some people have seen that, and some people won't. Has the generalization stuff been published?
Yes. Okay. Yeah. So we had a choral paper last year. We have a Agile paper under review currently.
Take a look. I need to learn more about it. I don't even know what the PAC-Bayes really means.
Okay. Well, I'll talk about it today. You can watch the video.
I agreed to do the student meeting before I realized that.
No, it's okay.
I can't bail on them. That'd be really not show up well at the. All right. Should we get started?
Yeah.
Oh, there's Mark.
Okay.
I'm happy to do it.
Hey, Mark.
So I'm going to go to the thing because I said I was going to go, and now I don't want to bail at the last second. So, but I can happy to introduce, or you can. All right, I'll do it, and then because I feel bad as well. So, all right. Thanks for coming, guys. So very happy to have Ani Majumdar from Princeton here. So Ani did his undergrad right here at Penn some time ago. So worked with Dan and others. After that, he went to MIT for his PhD, where Ani and I sat next to each other for 5 years. And he's one of the most brilliant people I've ever had the pleasure of working with. So super excited to have him here today. After MIT, I did a postdoc at Stanford and is now assistant professor down the road at Princeton, running the IRON lab. I guess, let's see, won Google Faculty Award, Research Award, an Amazon Award, Siebel Scholar, going off memory here. Really, really fantastic work. So very excited to have Ani here.
All right, thanks very much, Mike. So it's really exciting to be back here. So I skipped many classes to attend the grad seminar back when I was an undergrad. So it's really exciting to be back giving a grasp seminar. So the work I'll present today is some of the work we've been doing in my group on making guarantees on safety and on generalization for learning-based control of robots. So the main kind of problem we've been thinking about is this really fundamental problem of generalization. So let's say you have an unmanned aerial vehicle, so UAV, and you've tested this UAV out on a number of different environments. So let's say you've tested this out on 1,000 different environments. And let's say you found that it performs really well. The question that we're interested in is what happens when you place it in the 1,001st environment, so novel environment that the robot has never encountered before. Can we make guarantees on its performance? Maybe with some high probability it won't collide with anything. So this problem of generalization is really ubiquitous across many robotics applications. So if you're thinking about manipulation, for example, you might train your neural network control policy on a large data set of objects. But again, the question we're really interested in is what happens when the robot encounters a new object that wasn't part of the data set. How can we guarantee that the policy we learn will generalize to novel objects? So there are a number of really fundamental technical challenges associated with this problem of generalization. So first is that the dynamics of the system itself could be nonlinear, could potentially also be hybrid. The second is that the environment that the robot will operate in is unknown a priori. So I'm using the word environment kind of broadly here. So if we're thinking about navigation, you can think about the obstacles in the environment, obstacles as being the environment. If we're thinking about manipulation, then maybe the object is the environment. The robot might also have a rich sensing modality, so for example, vision or depth. And this often makes analysis challenging. So dealing with high-dimensional sensory inputs and making guarantees on that is a challenging problem. And finally, many of these systems will have learning as part of the control loop. So you might have a control or perception architecture that has a neural network embedded in it. And that again makes it really challenging to guarantee generalization to novel environments. So there's been a lot of work addressing many of these challenges. So a lot of work in robust control, reachability, chance-constrained programming tries to address the challenge of having uncertainty in the dynamics of your system. And while these approaches are extremely powerful, extremely nice conceptually, they typically assume a model of uncertainty. So you need to write down some kind of explicit model of uncertainty that your system will encounter. So for robust control or reachability, you might need to specify a set of worst-case disturbances that your system might face. If you're thinking about chance-constrained programming, you might specify a probability distribution, so a generative model over your uncertainty. And while this is often possible to specify these uncertainty models in settings where you're reasoning about the uncertainty in the dynamics of a system, it's really hard to specify uncertainty models when you're reasoning about the uncertainty in the environment that the robot will operate in. So think about how you would specify a probabilistic model over all possible buildings that your robot might navigate through. So that's a challenging task. So one way to deal with environments that are unknown a priori is to do real-time planning, to do receding horizon control. And one way you can make safety guarantees in this context is to assume that your robot has some emergency maneuvers that it can deploy and remain safe. So in the context of navigation, you might assume that the robot can come to a halt or to deploy a loiter circle that will maintain safety of the robot. Or you might make certain assumptions about the geometry of the environment. So for instance, obstacles are always separated by some distance. And these kinds of assumptions might allow you to prove that your robot can navigate through these environments without colliding with probability 1. But unfortunately, a lot of these assumptions about the geometry of the environment or about having maneuvers that you can always deploy to remain safe, these are often unrealistic assumptions, and real-world environments typically don't satisfy these. And I think asking for probability 1 kinds of guarantees, so your robot will never collide no matter what environment it's placed in, I think that is often too strong of a thing to ask for. And maybe asking for probabilistic guarantees instead is more reasonable. So one way to make probabilistic guarantees is to place everything in the framework of PAC-Bayes and to think about the environment as being part of the partially observable state. And while this is a really nice conceptual framework, computationally things get interactable very, very quickly, especially if you're thinking about environments as being part of the partially observed state. And typically you're forced to make certain approximations, which then makes it really hard to make guarantees on the resulting control policies. So the approach that I'll present today are essentially first steps that we've been taking towards addressing some of these challenges and making guarantees on generalization to novel environments. Okay, so let me first state the problem a little bit formally before we before I describe the approach. So I'll assume that your system has some dynamics. So X is the state of your system, U is the control input, and E is the environment that the robot is operating in. And again, I'm using the word environment kind of broadly to mean things that are external to the robot. So imagine buildings if you're thinking about navigation, or objects if you're thinking about manipulation. And the main assumption that we'll make, at least for now, so I'll relax this assumption a little later, but we'll assume that there's some true but unknown distribution from which your environments are being drawn, and that you have some samples from this distribution, some IID samples, and that forms your training data set of environments. So if your robot has a sensor, so potentially a rich sensing modality like vision or depth, then the goal is to synthesize a control policy, so something that maps sensor measurements or histories of sensor measurements to control inputs in order to minimize some cost. So I'll assume here for some technical reasons that the cost is bounded, and without further loss of generality, I'll assume that the costs are bounded between 0 and 1. And the final assumption is that for any given policy, we can evaluate the policy, so we can evaluate the cost of that policy just on our training environments. So if you have a simulator where you can simulate policies running on different environments, that's one way to satisfy this assumption. But potentially you could also do hardware trials on your training environments and satisfy this assumption. Okay, so our goal then is to synthesize a control policy that minimizes the expected value of the cost, where the expectation is taken with respect to this true but unknown distribution from which environments are being drawn. And in this work, we'll actually work with a slightly more general problem formulation. So instead of designing a single control policy, we're going to design a distribution, capital P, over control policies in order to minimize the expected cost. So the inner expectation here is because we're randomly selecting a control policy from this distribution P that we're trying to find. But really the main challenge is this outer expectation, which is the expectation with respect to this unknown distribution from which your environments are being drawn. So we're interested not just in minimizing the expected cost or minimizing the cost on the training environments, but we actually want to generalize to environments that are drawn from this true but unknown distribution. So the main technical idea behind our work is to leverage some ideas from generalization theory, from theoretical machine learning. So a lot of the development in generalization theory has been in the supervised learning context. So our main kind of technical contribution has been to take these ideas from supervised learning and translate them to the kinds of settings that we're interested in, which is learning control policies, so robotic settings, via a reduction-based approach that I'll briefly describe. So the upshot, so the main thing that this allows us to do is obtain upper bounds on the quantity that we're interested in. So upper bounds on the expected cost of policies or distributions over policies across environments that are drawn, again, from this true but unknown distribution. And our algorithmic approach is then to find policies that minimize this upper bound. And we can do this using convex optimization in certain settings or using stochastic gradient descent in more general settings. So the specific generalization theory framework we work with is called PAC-Bayes Theory. So PAC stands for probably approximately correct. And again, most of this framework has been developed in the supervised learning setting. And it actually provides some of the tightest known generalization bounds for classical supervised learning approaches, such as support vector machines. And more recently, so over the last year or two, there's kind of been a resurgence of interest in PAC-Bayes in particular in order to explain and promote generalization for deep neural networks. So if you haven't seen PAC-Bayes, so I want to make sure everyone leaves this talk with at least the main kind of result, the technical result from PAC-Bayes. So I'll describe it first in the supervised learning setting, and then I'll talk about how to translate that into the policy learning settings that we're interested in. So in the supervised learning setting, let's say we have some input space Z. So you can think of that as the space of all images. And you have some label space Z prime, which you can think of as object categories. And again, the primary assumption is that there's some true but unknown distribution from which your inputs, so from which your images, for instance, are being drawn. And we have some hypothesis class, so maybe neural networks parameterized by weights W. And we have a loss function that tells us how well hypothesis does on any given input. And so PAC-Bayes theory then applies to algorithms that have this very general structure. So before we do anything, before we see any data, we'll first specify a prior distribution over our hypothesis space. So we'll specify some P0 over our hypothesis space. We then observe some data samples that are drawn from this unknown distribution, and that's our training data. And then we find a posterior distribution that could depend on the training data that you observed, and potentially also on the prior that you picked before observing any data. So this is a pretty general kind of structure of a learning algorithm. And one thing that's worth pointing out here is that these priors and posteriors don't necessarily have to be Bayesian priors and posteriors. So you don't have to do exact or approximate Bayesian inference. So you can if you want to, but the results I'll present will hold for any priors and posteriors, as long as you pick the prior before having observed any data. So if we define our training cost as the training loss as the loss of our distribution over hypotheses over our training data, and if we define our true expected loss as that's kind of the main quantity of interest, so this is the expected loss across inputs. So that's the outer expectation. The inner expectation, again, is because we're choosing distributions over hypotheses instead of a single hypothesis. So the main result from PAC-Bayes is the following upper bound. So with probability 1 minus delta over the sampling of your training data, so delta is some parameter that you can specify, this upper bound holds on your true expected loss. So you can upper bound the true expected loss as a summation of the training loss and a term that sort of looks like a regularizer. So the regularizer, the main term there is this KL divergence term, which is trying to say that your posterior distribution is not too far away from the prior that you picked, and too far away is quantified in terms of the KL divergence. Dan?
N is the cardinality of X. What is capital N?
Capital N is the number of training data points you have.
So it's different than the cardinality of X. It's different.
That's correct. Yeah. So here the cardinality. So it doesn't even have to be like a finite number of hypotheses. You can have a continuously parameterized hypothesis space. So if you're familiar with VC dimension type bounds, then typically there's a cardinality dependence here. So instead of that, there's a kind of more general complexity term for PAC-Bayes, which is the KL divergence. So it's not just the cardinality. Yeah, so maybe I'll pause here for just a second and see if there's any other questions. So this is the main result from PAC-Bayes. If you have questions on that, maybe ask now. All right, so then the main kind of technical idea behind our work is to take these results from the supervised learning setting and translate them into the policy learning settings that we're interested in. So in the supervised learning setting, again, let's say we have some input corresponding to an image. Let's say we have a hypothesis which takes the input and maps it to some object category. We have our loss function which tells us how well a hypothesis did on a given image. And PAC-Bayes theory then allows us to come up with an upper bound on the expected value of the loss across different inputs drawn from this distribution, unknown distribution. So we can essentially map the policy learning setting onto the supervised learning setting by making the following correspondence. So we think about the environment as corresponding to the input. We think about our control policy as corresponding to our hypothesis. So the control policy essentially maps the environment through sensor measurements into a control action. We think about the cost function as just corresponding to the loss in supervised learning. And essentially with this correspondence, with this analogy, we can take the results from PAC-Bayes and directly translate them into a policy learning setting. Of course, I'm hiding some technical details here. So instead of picking a single action, really there's a temporal aspect to our problems. But this is the rough idea, the rough idea that allows us to take the results from supervised learning and kind of directly apply them to the policy learning setting. So the main result of that is, again, if we define our training cost as kind of being analogous to in the supervised learning setting. So our training cost is the cost of our policy or our distribution over policy evaluated on our training environment. So that's something we can potentially evaluate. The true expected cost is the quantity that we're interested in. So it's the expectation taken with respect to this distribution over environment. The result that we get is that with probability 1 minus delta or the sampling of your training environment, we have this upper bound. So we can upper bound the true expected cost as a summation of the training cost and this term that again sort of looks like a regularizer. And so this gives us a guarantee on our true expected cost. So if we chose this distribution P over control policies, then we can guarantee that the true expected cost across environments is upper bounded by the right-hand side of this inequality. So the algorithmic approach then is to try to find distributions over policies, distributions P, that minimize this upper bound. And for the settings where we're working over a finite control policy space, we can do this via convex optimization. And for more general settings where we have continuously parameterized policy spaces, so policies parameterized by neural networks, then we can do this optimization, so minimize this upper bound using more general techniques like stochastic gradient descent. So I'll talk about the finite case first. So let's say we have some finite number of policies, and our goal then is to find a distribution, so finite, so discrete probability vector over this finite space. So minimizing the PAC-Bayes upper bound then corresponds to solving this optimization problem. Dan?
So I'm worried that in general, particularly in the neural net
Yeah.
setting, it may be very hard for you to even know anything about the KL divergence between the thing going in and the thing that you compute.
Okay, so I'll talk about them in just a second actually. So here in the finite setting, so when we're working over a finite policy space, of course we can just write it down explicitly. And then I'll talk about the continuous setting in just a minute. So yeah, in the finite policy setting, this is the optimization problem. So this corresponds to the training cost, and this is our regularizer. And the constraints are just ensuring that the vector P is a valid discrete probability vector. So yeah, it turns out that we can solve this optimization problem, the problem of finding a P that optimizes this quantity via convex optimization. And in particular, using a relatively recently studied class of convex optimization problems called relative entropy programs. So the main constraint that a relative entropy program can handle is a constraint of the following form. So let's say we have mu and nu, which are decision variables, which are vectors, and we have some lambda, which is a scalar decision variable. Then the constraint that we can enforce is that the KL divergence between mu and nu is upper bounded by lambda. So constraints of this form are kind of the main constraint that a relative entropy program can handle. We can also throw in some linear equality and inequality constraints. And the objective, the cost function, has to be linear in the decision variable. That's kind of the standard form of a relative entropy program. And yeah, you can solve these pretty efficiently using interior point methods. There's actually a number of solvers that are out there, commercial solvers like Mosaic and so on, that you can just plug in a relative entropy program and it will use an interior point method to solve it.
Where's the environment dependence?
Right, so the environment dependence is here. So this is the training cost. So it's the cost of your distribution over policies evaluated on the training environment. Yeah, so we don't assume that we have knowledge of this underlying distribution from which environment will be drawn. We just assume indirect access to it in the form of some training environment, some examples. Yeah. So yeah, I've kind of hidden it here. This is where the environments come in. So yeah, it turns out that relative entropy programs are a pretty general class of convex optimization problems. So if you've heard about linear programs, second order cone programs, geometric programs, it turns out that relative entropy programs subsume these classes of convex optimization problems. And there's also an interesting relationship to semi-definite programs. So what's relatively easy to show is that relative entropy programs contain things that are not directly expressible via semi-definite programming. What's not known, so what's something that's an open question, is the converse, so whether you can have semi-definite programs that you cannot directly express using a relative entropy program. So either the picture looks the way I've drawn it here, or it looks like this. But either way, these REPs are a pretty broad and interesting class of convex optimization problems. So for us, what they help us do is solve this optimization problem So the main kind of interesting term in this optimization problem is the KL divergence between the posterior and the prior. So we can massage this optimization problem into a form that you can then tackle using relative entropy programming. So yeah, that's kind of the story in the case where you have a finite number of policies that you're then finding a distribution over to minimize the PAC-Bayes upper bound. So now I'll talk about the more general settings when we have continuously parameterized policies. So let's say parameterized, so policies that are neural networks parameterized by weights W. So what we're going to do here is to specify distributions over policies by specifying distributions over weights. And specifically, we'll specify Gaussian distributions over the weights of a neural network. So what that allows us to do is answer Dan's question, which is now for Gaussian distributions, multivariate Gaussians, we can compute the KL divergence in closed form. And essentially then what we can do is find a mu and a S, so a mean and a covariance matrix, so a distribution over policies that minimizes the upper bound that we get from PAC-Bayes. And we can do this using stochastic gradient descent or kind of black box optimization techniques. So there's one technical challenge here, technical difficulty here, which is that in order to evaluate the training cost, so the cost associated with the distribution fee on our training environment, there's this expectation over policies, and that might be challenging to evaluate. So we kind of resolve this just by sampling policies from the distribution and using some concentration inequalities. So this is a similar technique to what was used in this paper by Zugati and Roy in the supervised learning setting. But yeah, so the kind of summary is that we're finding a distribution over policies, a distribution defined by the mean and diagonal covariance of a Gaussian in order to minimize the bound that we get from PAC-Bayes. All right, so yeah, we applied this technique on a number of different examples, and I'll present some of the results here. So the first one is an obstacle avoidance example. So this is a ground vehicle model, so a Dubin's car type model, equipped with a range sensor. So the range sensor gives the robot depth measurements in 20 different directions. So we simulated the dynamics and the sensor using the PyBullet simulator. And our goal is to learn a reactive obstacle avoidance controller, which has a very simple form. So it's simply taking a linear combination of 1 over the depth measurement. So it's saying if there's a bunch of stuff on my left, then I should turn right. If there's a bunch of stuff on my right, I should turn left. So very simple reactive obstacle avoidance controllers, which often really work well in practice. You can tune up these controllers and get good performance. But typically it's hard to make guarantees on how the controller will perform on some environment that you didn't test it out on. So these are some videos, some trials of the policy that we learned on novel environments, so environments that were not part of the training data. So we fixed some number of training environments that we then used to find a distribution over control policies using our PAC-Bayes bound. And this is the policy or the distribution over policies running on novel environments that were not part of the training data. So you can see that sometimes it crashes, but most of the time it does pretty well. Dan?
If you have environments that are densely cluttered, you're going to get convex traps, even with very simple constituent obstacles.
Correct, yes.
And these simple schemes can't possibly.
That's right, yeah.
So where does that show up in?
Yeah, so it doesn't, so I guess it doesn't show up here, but there's nothing, I don't know if there's anything fundamentally different there in terms of the conceptual approach.
Can I push back?
Sure, of course.
So,
Yeah.
like, if you have this Gaussian assumption, then you can't allow multimodal opposites, right? Where you have to decide whether this is a highly non-convex environment or
Right.
it's a very simple convex environment.
Okay,
So
yeah.
haven't you sort of buried that buried that under the carpet in a way that's going to haunt you later?
So for this example, I would say that we have. So we're just finding these simple reactive policies. So what we're currently working on is to do some kind of planning as part of so have a planner essentially as part of the control policy. So the simplest, I think, way to implement it is to assume that you have a finite number of motion primitives, so going straight, turning left, going right, and so on. And the policy essentially just picks one of these primitives and replans in a receding horizon fashion. So it's a more complicated class of control policies.
Maybe I should say this again. How hard is it going to be to get rid of the Gaussian premise and use a more general class that supports multimodal?
Yeah, I don't know if it's too hard. I mean, I think the main thing that you need is to compute the KL avoidance, right? So the Gaussians are nice because you can compute KL avoidances in closed form. But for Gaussian mixture models, you can't compute the KL avoidance in closed form, but you can compute upper bounds on it. So I'm optimistic. I don't think we're fundamentally limited to Gaussians, and I think we can have multimodal distributions as well. But definitely in this example, we have not done that. So it's Gaussians, it's reactive, and the non-convex environments will mess this up. But what we're able to say is that we're able to guarantee the performance of the controller on novel environments. So this table is, the top row of the table is showing the number of environments we use for training. The middle row is the bound that we obtain on the success rate via PAC-Bayes. And the bottom row is the true estimated success rate obtained just by exhaustively running the policy that we learned on different environments. So as you can see, even with a relatively small number of training environments, we're able to get some reasonably strong guarantees on generalization performance. And as you increase the number of training environments, the bounds improve, and moreover, the difference between the bound and the true estimated success rate gets pretty tight. So for 10 to the 4th or 10,000 environments, we're able to guarantee a success rate of around 90% or so. So we also applied this on a slightly more challenging example. So our goal here was to demonstrate that we're able to get some reasonably strong generalization guarantees for control policies based on neural networks. So we applied this to our framework to a grasping example where we simulated everything, again, using the 5-bullet simulator. And we had a RGBD sensor that we were simulating. So we used 2,000 training objects from the ShapeNet dataset in order to train a neural network policy. So these are some representative objects from the ShapeNet dataset. So we randomized masses, inertia as initial conditions. And this is the rough kind of architecture of the neural network policy. So we parameterize a graph using its XY location and just the yaw orientation of the end effector. So we first try to estimate the center of mass of the object, so just the centroid of the object. And then we also take the depth image, we colorize it, and we pass it through a pre-trained VGG16 network. And then we have a few fully connected layers. And then at the end, we just combine the output of the neural network with the centroid estimation, and that's our final predicted graph. So these are results. So again, we applied our PAC-Bayes framework again in this more complicated setting where we're learning neural network-based control policies. And these are examples of the learned policy on novel objects. So in this setting, we're able to make a guarantee of around 71% success rate on novel objects. And empirically, again, if you just run the policy on lots and lots of different objects, the empirical success rate is around 81%. So of course, there's still some way to go here. So these bounds are reasonably tight, but could potentially be improved. But I think it's really exciting that we're able to get pretty strong generalization guarantees for neural network-based control policies, and that's traditionally been really hard to do. Okay, we also have some hardware experiments that we've been recently doing. So these are some videos just from a couple of days ago, which are, let's see. Yeah, let me play that again. Yeah, so this is the Parrot swing drone. So it takes off vertically and then transitions to forward flight in order to fly fast. So this is in a Vicon motion capture system, but we're simulating a depth sensor. So the drone isn't using its kind of absolute position information. We're pretending like it has a depth sensor. And we are implementing a reactive obstacle avoidance policy, kind of similar to the one I showed for the ground vehicle model. And yeah, again, we applied our approach, learned a policy using our PAC-Bayes bounds, and this is the policy running on different environments. Show the sound maybe. Yeah, so it's still work in progress. We're trying to do a more kind of thorough experimental evaluation, compare the bounds that we get from PAC-Bayes to these real-world experiments. Question?
This probability case here is discrete or continuous?
So here we did the discrete version.
Just discrete, how many different values?
Yeah, I think it was around like maybe 50 or 100 different control policies. But yeah, we could do
100.
yeah some on that kind of magnitude control policies.
So what's the kind of largest number you tried for the discrete?
For the discrete case, we haven't scaled it that much. I mean, it's roughly around that number. But I think the convex optimization problems are still pretty small, so we could probably do like a few thousand maybe.
I'm wondering about whether there would be like vanishing gradient issue for the policies.
So if you have finitely many policies, it's not an issue there because it's just a convex optimization problem. And yeah, I guess in the more like general settings where you have continuously parameterized policies, it's not a finite number, so I don't think you have the vanishing gradient issue. So yeah, okay. One big assumption that we've made so far is that our this true distribution from which environments are being drawn, and training and test environments are drawn from the same underlying distribution. So one natural question is what happens when your training distribution is different from your test distribution, so there's a distribution shift. So there's, again, a lot of work on these kinds of questions in the supervised learning setting. So work in domain adaptation, for example, and distributional robustness. So what we've been doing is essentially trying to tackle this question using the lens of distributional robustness, where the setting is the following. So we assume that we have some distribution from which the training environments are being drawn, and we have some distribution from which the test environments will be drawn. And we have to make some assumption about the relationship between training and test environments. And we'll assume that the KL divergence between the test and training distribution is bounded by some value B. And you can generalize this not just to KL divergence, but to other divergences like F divergences or the Wasserstein distance. And the main kind of technical hammer that we use is to use the Donsker-Verdon change of measure formula, which basically allows us to upper bound the expected value of some random variable for us corresponding to the cost, where the expectation is taken with respect to D prime. So we can upper bound that using the KL divergence between B prime and D. And this term that sort of looks like the entropic risk. So if you're familiar with robust control, this should be a familiar quantity. So the KL divergence we assume is bounded by B. And this term we can bound using the PAC-Bayes bounds that I presented before, because this depends only on the training distribution. So we can work with the exponentiated costs instead of working with the costs, and obtain a bound on this quantity and take the log of that. And that gives us a bound on how well our policies will do, what the cost will be on the test environments. So we apply this again on the obstacle avoidance example. So here there's a training distribution and a test distribution that differs in the way the obstacle radii are sampled. So the training distribution over the radii is shown in blue. The test is shown in orange. And the main point here is that the test distribution is harder in the sense that during training you see a lot of obstacles which have a small radius. During tests you see more obstacles that have a larger radius. And these are the numerical results. So again, the top row is the number of environments we use for training. This is the robust bound that we get on success. So if we assume that there's this upper bound on the KL divergence between training and test, this is the bound that we obtain. And this again is the true estimated success rate. And as you can see, again, these bounds are reasonably tight, so not as tight as the case where training and test distributions were the same, but still potentially useful in practice. So there's a couple of important challenges with this framework. So one assumption that we made is that we have some upper bound on the KL divergence between the test and training distributions, and coming up with those upper bounds might be a challenging endeavor. But moreover, even if you can come up with an upper bound, this quantity could be extremely large. So I'll give you a simple example. So let's say during training, all your environments are colored a certain way, so maybe all of them have a red color, and during tests, all of them have a green color. So this KL divergence between the training and test distributions will capture that variation, right? And you'll have some large KL divergence. But of course, intuitively, we know that the color, if we're just doing obstacle avoidance, is completely irrelevant, and we shouldn't care about that difference. So there are some differences that matter, some differences that don't, and color is one that doesn't matter. So the key kind of approach, the key technical idea we've been pursuing to address this challenge is to come up with perception and control strategies that are task-driven, in the sense that we want to synthesize controllers that are minimalistic and only depend on a few features of the environment and make lots of things irrelevant. So we want to make the colors of objects, of obstacles, irrelevant if you're just doing obstacle avoidance. Okay, so that's what I'll spend the rest of the talk talking about. And just to kind of make sure that we're on the same page, so I'll start off with a simple example. So let's say you want to design a robot in order to catch an object, so maybe a ball that you throw at it. So one strategy would be to use the robot sensors in order to do full state estimation. So you estimate the state of the robot, you estimate the state of the ball, so positions and velocities. You write down the equations of motion for ballistic motion. You integrate the equations of motion forward, predict where the ball will end up, and you use a RRT or some kind of a trajectory generation scheme to design a trajectory that will go and intercept the trajectory of the object. So this might be a fine approach, but it turns out if you study how humans do this task, and also animals like dogs catching frisbees, the kind of strategy we use is fundamentally different. So it goes by the name of the gaze heuristic, which essentially amounts to fixing your gaze on the object and modulating your speed to keep that gaze angle at a constant value. So you can convince yourself that as the object is falling, if you can keep that gaze angle at a constant value, then this forces you to go and meet the trajectory of the object. So this is a dramatically simpler strategy. So you're modulating so estimating and modulating a single variable, which is this gaze angle, instead of estimating and modulating the entire state of the system, which would be much higher dimensions. And it turns out actually humans use this kind of strategy for more complicated decision-making tasks as well. So the pilots of the US Airways flight that landed on the Hudson River used a similar strategy to decide whether to land at LaGuardia Airport or whether to take their chances and land on the Hudson River. So this is a quote from the co-pilot. So he said it's not so much a mathematical calculation as visual. So when you're flying in an airplane, a point that you cannot reach will rise in your windshield, and a point that you're going to overfly will descend in your windshield. So they fixed their gaze on the control tower of LaGuardia Airport and found that the tower was rising in their windshield, and realized that they weren't going to make it, and decided to land on the Hudson River instead. So our goal here is to automatically synthesize these kinds of minimalistic or task-driven representation. And the framework I will describe here is slightly different from what I described in the first part of the talk. So I'll describe things here in a model-based setting. So we'll assume that we have some model of the system described as a partially observable Markov decision process. And the key technical tool that we use is the notion of information bottlenecks, which was originally developed in the information theory literature. And our approach then has two phases. So there's the offline phase where we synthesize the task-relevant representation, so figure out what variables are relevant. And the way we do this is by finding this intermediate representation, these task-relevant variables, that form a bottleneck between the full state of the system and the control inputs. And then online, we use our sensor measurements to only estimate the task-relevant variables. So in the ball catching example, maybe think of the gaze angle as the task-relevant variable. But the point here is to automatically discover these task-driven representations. So a little bit more formally, so the offline phase, what we do is the following. So given some Markov decision process model of your system, we synthesize two mappings. So we synthesize a stochastic mapping from the state to this task-relevant variable, and then we synthesize another mapping from the task-relevant variable to control inputs. So our control policy only depends on the task-relevant variable. And specifically, we synthesize these two maps in order to minimize this objective. So this term here is kind of standard, so that's just the expected value of the cost over some finite horizon. So that's what you would do in a standard kind of MVP formulation. This is the interesting term. So what this is doing is minimizing the mutual information between the state and the random variable corresponding to the task-relevant variable. So intuitively, the mutual information captures how independent two random variables are. So this term in the objective is trying to make the task-relevant variables, the TRVs, as independent of the state as possible. So this is kind of what's forming a bottleneck between the states and control inputs. And then in the online stage, once we've synthesized the task-relevant variables, we use our sensor measurements to do Bayesian filtering on just the TRVs. So we don't estimate the full state of the system, but instead we only estimate these task-relevant variables. So there are a couple of potential advantages to doing task-relevant estimation, perception, and control. So maybe the obvious one is computational efficiency. So when you're implementing these controllers online, you don't need to maintain beliefs over the full state of the system. You can simply estimate the potentially much lower dimensional task-relevant variable. The other potential advantage is robustness. And the intuition here is that if you're filtering out a lot of information from your state, if you're just throwing it away, then if you have uncertainty or noise that's corrupting those portions of your state, then you're kind of naturally robust to it because your actions don't depend on that. We have some formal results trying to characterize that, but at this point it's intuition. Dan?
Have you just postponed, this is advertised as automated synthesis, but you kind of postponed the problem into the design of this Q function class, right? I mean, pies are not that easy, but people have some experience and ideas about how to parameterize pies. But Qs is kind of a wide blue yonder unknown thing. It seems like you can be shifting the problem of it's not exactly automated once you have to figure out how to parameterize the tractable and computationally effective.
Yeah.
Here. Right?
Yeah, I think that's a fair point. So I mean, so far we've been working with simply kind of parameterized Qs, so just linear plus Gaussian, like those kinds of Qs. But I mean, I guess this kind of architecture is familiar in neural networks, right? So this is kind of a autoencoder type architecture. And maybe the simple answer would be to parameterize them using stochastic neural networks. And I guess that would be a rich class of functions parameterizing Qs and potentially tractable in the same sense that optimizing training neural networks is tractable. Question?
How do you model
Yeah, so we're assuming that we have like a Markov decision process model of the system. So you can, the simplest setting would be linear Gaussian setting, so your dynamics are linear, and then you have some Gaussian noise, but yeah, you might have more complicated like noise models as well. But yeah, we're assuming that we're given an MDP model of the system, and that has the uncertainty kind of described as part of it. It does explicitly model uncertainty. That's correct. Yeah, so we're assuming that that is specified here. Yeah, so this is not in the learning-based setting. This is in a model-based setting where we assume a model of the uncertainty as well. Yeah. So we applied this on a simple example. So this is a lava problem, so finitely many states. The robot occupies one of the cells at any point in time. It needs to get to the goal. There's a lava state which is absorbing, so if it gets to the lava, it just gets stuck there. So one strategy for doing this is to essentially assume the separation principle. So let's say we have some sensor that tells the robot which cell it's in, but it's a noisy sensor, so with some probability, it's going to report the incorrect cell. So you could do maximum likelihood estimation, figure out what's the state that I'm most likely in, and then just implement this control policy. So if I estimate that I'm in state 2, then I go right. If I estimate that I'm in state 4, then I go left. The problem with this, so assuming the separation principle, is that if you misestimate your state, so if you, let's say you estimate that you're in state 2, when in reality you're in state 4, what you're going to do is go right, and that's going to bring you to the lava, and that incurs a very high cost. So instead, if we apply our information bottleneck approach, get a control policy out of that, it does something pretty interesting. So it comes up with essentially a purely open loop policy which goes left 3 times and then goes right twice. So if you think about this, no matter which cell you start off in, if you go left 3 times, you're going to end up at cell 1, because if you try to go left from cell 1, you just remain in cell 1. And then you go right twice, and that leads you to the goal. So of course, this is a really robust strategy in the sense that we're throwing away all the information from our sensors, and any uncertainty that corrupts that we're going to be robust to. So we also applied this in a slightly more complicated setting. So this is a spring-loaded inverted pendulum model, common model for capturing running. And we, again, applied our information bottleneck ideas to come up with a task-relevant representation and a control policy that depends on that in order to get to some specified goal location. So after 3 hops, we should get to this location here. And we computed our controllers using linearizations of the Poincare map of the system. And it turns out for this task, the approach kind of automatically synthesized a one-dimensional TRV, so it took the full state of the system, which was pi-dimensional, and boiled it down to a single-dimensional variable that was sufficient to do reasonable control. So it was kind of a satisfying controller. And so the computational efficiency, I guess, is kind of clear. There's a single variable that you're trying to estimate online. And this is giving some evidence to the robustness story as well. So what we did was we compared our approach to ILQG, which is first doing kernel filtering, so estimating the full state of the system, and then doing LQR, ILQR. And what we did was we specified 2 models of the sensor. So one model which was the correct model, and the other which had an incorrect specification of the covariance matrix corresponding to the noise and the sensor measurements. So as you can see, the red is ILQG with the correctly specified model, and as you would expect, that does best. So ILQG is at least locally kind of optimal. But the interesting comparison is what happens when you specify an incorrect model. So the blue is ILQG with the incorrectly specified model, and the green is the performance of the controller that we get using our information bottleneck strategy. So this is a histogram of the cumulative cost, and as you can see, the ILQG with the incorrect covariance does worse than our task-driven policy. And again, the intuition here is that because we're throwing away a lot of information from the state. Then if we have uncertainty, then we're less affected by that. And we're also working on some hardware implementations. We have some undergrads build a ball catching robot. So our goal here is to compare the policies that we get, these automatically synthesized representations with the Bayes heuristic representation, which we know is pretty good for this stuff. Okay, so I just want to end, so I think we have about 5 or 6 minutes, to end with some directions for current and future work. So on the generalization theory side, I think maybe the biggest challenge, the thing that keeps me up at night, is coming up with really good bounds on out-of-distribution generalization. So most of what I described today was in the setting where the training and test distribution is the same. We have some directions, some bounds on the case where the training and test distributions are different. But I think there's still a long way to go on this problem. And one potentially promising direction is to think about causality. So the intuition here, or the idea, is that if you can learn features that are causally related to success, so causally related to your cost, then that causal relationship might be stable across different distributions and might allow you to generalize really well out of distribution. We're also working on improving the bounds that we currently have. So one approach that we're pursuing is incorporating priors that are derived from model-based techniques. So one of the nice things about PAC-Bayes is that it allows you to incorporate priors that you might have some domain knowledge, and that potentially improves the bounds that we obtain and the resulting performance as well. We're also thinking about generalization bounds for other settings. So imitation learning in particular, I think, could really benefit from having guarantees on generalizations. If you learn some policy from expert demonstrations, how do you guarantee that policy will generalize to settings that you didn't have demonstrations for? And finally, we're also thinking about the meta-learning setting, where you're interested in generalizing not just across different environments, but potentially across different tasks as well. So I mentioned, described some of our hardware implementation directions on the UAV side. We're also thinking about some problems in manipulation, particularly in aerial manipulation, which I think is an exciting domain. So on the task-driven perception and control side, one exciting direction is to do active task-driven perception. So kind of similar to belief space planning, where you take actions that reduce the uncertainty in your estimate of your state. But instead of reducing the uncertainty of the full state, you take actions that reduce uncertainty only over the task-relevant variables. And I think this is an important direction. We're also looking at some different formulations of task-driven perception and control. So our approach that I presented today was based on information bottlenecks, but I think potentially differential privacy is another way to formalize what we mean by task-driven. So the intuition here is that we want to make the mapping from states to control inputs differentially private, so we're hiding information from the state and still doing well in terms of our control task. And we think we might be able to get stronger theoretical results from this kind of formulation. And finally, as I think someone asked, so everything that I described on the task-driven perception and control side is in a model-based setting, but I think we can extend this to a learning-based setting as well. Okay, so I think I'll end here. So I presented our results on making generalization guarantees via PAC-Bayes theory, presented some algorithms based on convex optimization and stochastic gradient descent for learning policies with guarantees on generalizations. And I presented a number of examples showing that we're able to get pretty strong guarantees on generalization, even for control policies with neural network architectures. And finally, I presented our work on task-driven perception and control for coming up with controllers that are computationally efficient and robust. So hopefully I've convinced you that there's some exciting potential here for using these techniques to make guarantees on safety and on generalization for learning-based control of robotic systems. So if you're interested in learning more, so these are the papers. So the work on PAC-Bayes we presented at Coral last year. We have a general version that's currently under review. and the work on task